this recording has started again. So, on Thursday and Friday of last week, we talked about quantum numbers. What do quantum numbers do for us? Eric's good.
Define the sublevel.
Partially, but there's a little bit more we want to go with it. Nick, go ahead.
They tell us like where the electrons are.
Do something for me before we finish that answer, Nick. There's something about your answer that you have to change. Nick's answer tells you where electrons are. What do you have to change about that answer? Alexis, go ahead.
It gives the probability.
The probability of where electrons are, right? If I did this, if I did where electrons are, right, that would be okay, right? But do we know that those electrons are actually there? No. We have probability that they're in certain places, but the actual possibility is that they could be anywhere, right? Does that make sense? Okay. What do we call those places that have high probability of finding electrons? What do we call those areas? Orbitals. Orbitals, right? They're not like Bohr's orbits, right? They're not definite, but they're high probability. And those quantum numbers, like we said, are a way to describe those different areas, right? Based on the energy level that they're in, and then the sub-level, and the shape, and all those things we talked about on Thursday and Friday, right? Is that good? Now, today, we think about it this way.
Good morning, everyone. Excuse the interruption. Two things, actually. First, quick thank you for students this morning, and students who are dropped off, please thank your parents. Traffic was great. Best it's been in about 3 years as far as people getting onto our campus. We're very excited to have those lots. So thank you. Students did a great job driving. You were patient with people, and I think we're in a much better place than we were on last day last week. Only negative comments to share. If you are currently in the brand new student lot without a tag, you risk being towed this morning. So if you are out there and you are not tagged, they will begin towing this morning and enforcing those tags. We are limited on spots until they finish the edges of the lot. We have plenty of spots for what we have now. We'll be doing a count second period and selling off the waiting list to get every student into the lot that we possibly can. But we'll be waiting about a month for 25 more spots. And because we are tight, we will be enforcing the tag. So if you are out there with a counterfeit tag, they will probably find it today and tow your vehicle. If you are out there without a tag and you go out at dismissal and your car is gone, please come to the office. We can give you directions to patent towing. Everybody have a great day. We will see you tomorrow. That's the end of the day announcement. Scratch that. Have it.
I don't know what that just meant, but how was the parking lot this morning? Was it all right? Or I got here early enough that there's like no cars, so it doesn't. All right, where was I? Okay, so today, what we do today is this. We can think of all of those orbitals that exist around the nucleus of an atom, areas of higher probability of finding electrons, kind of like an apartment building, okay? There is a structure, and all of these apartments exist within that building. But just because the apartments are there, does that necessarily mean that people live in those apartments? Is it possible that some of those apartments might not be rented, or like a hotel room, right? Is it possible that some of those hotel rooms might not be filled? They're there, but just because they're there doesn't mean that electrons exist within those areas. And that's what we're going to talk about today. How do we determine which areas electrons are most likely to be in out of those areas where they all could possibly exist? Okay? That make sense? So it's a bunch of empty rooms right now. All those orbitals are a bunch of empty rooms. Now we're going to fill those rooms. But there's an order in which those rooms get filled. And the main driving factor behind that order is something we call the Aufbau principle. Okay? The Aufbau principle, like so many other things that we are going to deal with in this class, is based off of energy. Orbitals are filled from lowest energy to highest energy. So orbitals that represent areas where electrons would have the lowest energy get filled up first. And then orbitals that have the next lowest energy get filled up second. And then orbitals that have the next lowest energy get filled up third. So just like so many other things that we do in here and that we will continue to do throughout the whole year, energy is the driving force behind it. And generally that means we go from low energy to high energy. Okay? We call that the off-bow principle. Orbitals that are closest to the nucleus contain lower energy, right? That's an idea that Bohr threw out when he first made up his model of the atom. While his model wasn't completely right, that idea of orbitals closest to the nucleus, lower energy, orbitals farther away from the nucleus contain higher energy, that's still the case, all right? So we're going to fill orbitals closest to the nucleus first, then go out, okay? And lucky for you, so you don't have to memorize it, although you'll see that a pattern definitely starts developing. On your outline are two separate charts. Both of those charts represent the same thing. So if you look at the one on the left is the one I like more. That's one I'll kind of reference more often. If you look at the one on the left, right, it's kind of a graph. Not exactly, but kind of. What do you see along the left-hand side of that graph? What is it telling you there? Right? Here's good.
Increasing energy of electrons and orbitals.
Increasing energy of electrons in orbitals. And there's an arrow that points upward. Meaning, Eris, according to the off-bow principle that I just had you write down, where are we going to start this chart? At the bottom. Because orbitals get filled from lowest energy to highest energy. And if this is saying increasing energy, we're going to start at the bottom and go up. Okay? So you'll see that there's a pattern that starts developing, and you'll see that pattern here pretty soon. But there are a couple more rules along the way that we're going to have to deal with. Okay? So this chart, sorry, it's not on page 147 of your book. That's an old book. So don't write that that's on page 147 because it's not. Okay? But how we fill this is, this chart we use in order to make us an orbital diagram, right? So we've been introduced to the idea of an orbital. What's an orbital again? What do we describe an orbital as? Right? Mark, go ahead.
The areas of high probability of where we might find an electron.
Areas of high probability where we might find an electron. So an orbital diagram then tells us how electrons are distributed within those orbitals. The orbital is an area of high probability. It's an area that exists around the nucleus. But, as we'll see here, not all orbitals are created equal. Just because we say that it's a high probability, some orbitals have higher probability than other orbitals. And that's based on the energy of the electrons within those orbitals. Okay? So, an orbital diagram, depending on what book you look at and what source you read, can either be circles or lines or boxes that are used to represent the different orbitals, and then arrows are used to represent single electrons. All right? So on your outline, you have a couple of examples. These are what we refer to as examples of orbital diagrams. They are not full orbital diagrams. They are representative of what orbital diagrams look like. We are going to start drawing orbital diagrams starting as soon as I flip this slide. Okay? So, some books use circles, some books use just lines, some will use dots. I like to use just straight lines because they're a lot faster to draw if you're drawing them by hand. So that's fine, you can do that too. If you really want to draw the circle, that's okay. All right? All right. More importantly than what orbital diagrams are, though, let's talk about how we determine the orbital diagram for an atom. So let's start off with the simplest atom we can get to, right? hydrogen. So, first, we got to find hydrogen on the periodic table. Hydrogen's pretty easy to find on the periodic table. Everybody find it? Okay. What's hydrogen's atomic number? 1, right? And hydrogen's atomic number being 1 tells us 2 things about that atom. What are the 2 things that its atomic number being 1 tells us? Come on, I know somebody besides Eris knows. Okay. Suzanne, go ahead.
Has one electron and one proton.
1 proton, 1 electron. So, if we're going to draw an orbital diagram for hydrogen, all we have to do is account for 1 electron. Okay? So, as we just discussed, the off-bow principle tells us the order in which orbitals are filled. Orbitals are going to be filled from low energy to high energy. The lowest energy orbitals are going to have the highest probability of being filled, and so on. Okay? So, you go back to your chart that's on the front page, right? So if you flip the page down at the bottom, okay? Back on the front page, check out the chart. And Eris, you said we were going to read this chart from where to where?
Bottom to top.
From bottom to top. So, if we go back here, let me do this. And take this. And I'm going to put that there. Put that on its own page right there. And then, so, we said that right now we're looking for hydrogen, right? And hydrogen has 1 electron, okay, because its atomic number is 1. So, like Eris said, we go from bottom to top. So we start at the bottom here, and we go up, and what's the first orbital that we run into? 1s, right? What can you tell me about an orbital that we have called 1s? From our discussion last week, what can you tell me about an orbital that we call 1s? Here, let's do this. Discuss with the people around you. There's 2 things that you should be able to tell me about a 1s orbital based on the fact that we call it 1s. Discuss with the person next to you. Go. 2 things. Okay. So, let's discuss. So, the fact that we call this orbital 1s, 2 things you should be able to tell me about it. What are the 2 things you should be able to tell me about this 1s orbital? What's 1 thing you can tell me about it? Okay. Mark, go ahead.
It's going to be the first suborbital in the first energy shell.
So it's the first sublevel in the first energy shell. And for the first energy cell, Mark, are there any more sublevels within that energy shell?
No, there are not.
No. It's only 1, okay? So where is this orbital located? Within the atom itself. Where's it going to be? Go ahead.
Close to the nucleus.
Close to the nucleus, okay? What else can you tell me about this orbital, especially the fact that it is an s orbital? Eris, go ahead. It's like a spherical shape, right? So that's going to be the shape of this orbital because all s orbitals have that spherical shape, okay? Now, that's the case, but big picture-wise, we really don't care too much about that when we're drawing this hydrogen orbital diagram. All we do to represent the 1s orbital is draw ourselves a line, okay? Could be a box, could be a circle. I like drawing lines just because it's easier to draw up on the board. And then we label that line with which orbital it is. So we call it 1s. All right? That is the orbital that has the highest probability of finding electrons. And then like we just wrote down, how do we represent those electrons within that orbital? What do we draw to represent the actual electron itself? There's arrow. Okay? A lot of times you'll see them drawn as one-sided arrows, mostly just to save space, but so we would draw an arrow to represent that one electron within the 1s orbital. Okay? And this is the orbital diagram for hydrogen. It tells us where hydrogen's electrons are most likely to be located. Okay? Good there? Questions? Okay. Next. Next one we come across is helium. Okay? So, you go to your periodic table and you find helium. Helium's pretty easy to find as well. Okay? Everybody find helium on their periodic table? Top right-hand corner, right? What's helium's atomic number? 2, right? And Suzanne, that means what?
There's 2 protons and 2 electrons.
So 2 protons, and more importantly for our purposes here, 2 electrons, right? We know where the protons are going to be. They're going to be in the nucleus. But the electrons are a little harder for us to get a hold on where they're going to be, quote-unquote, located, right? So we said that the off-bow principle still applies, lowest to highest. So we said that Eris reading this chart, what's the lowest energy orbital that we come across?
1s.
1s, right? So we start off and we draw our line, we label it 1s, okay? Now we know that we have to place 2 electrons, okay? So we draw our 1 electron just like we did with hydrogen, okay? But then the next principle that comes up talks about where this next electron goes. On Friday, we introduced the idea that while orbitals are areas of high probability, can they be overcrowded? No, because we said these areas of high probability are a balance between being attracted to the nucleus, but then repelling all those other electrons, right? So we said that there's a limit to each orbital. And what is that limit to each orbital? Go ahead, Mark. 2, right? Each orbital can hold 2 electrons. Right now, this orbital, 1s, only has 1 electron in it, right? So that means it has room to accommodate another electron. And it will, okay? But we have to distinguish the 2 electrons. Remember we said that no 2 orbitals or no 2 electrons can have the same set of quantum numbers, right? We have to identify all these different areas one from the other. Just like your house has a specific address that identifies it from all the other houses, okay? But one more idea that we use to distinguish these electrons is the Pauli exclusion principle. So the Pauli exclusion principle states that each orbital can contain only 2 electrons, a maximum of 2. And we have to distinguish these electrons from one another. On Friday, we talked about the idea of the spin quantum number. And we said the spin quantum number has 2 possible values, +1/2, -1/2. That's how numerically we distinguish these different electrons from one another. On an orbital diagram, we distinguish these electrons from each other by the way the arrow points. So, one arrow up, if there's another electron within that orbital, we draw that arrow pointing downward. So, back to our orbital diagram, right? There's electron 1, there's electron 2. Okay? Good there. Questions? All right. Next. Next element we come across, lithium. So, we find lithium on the periodic table, right? Lithium's atomic number is what? 3, right? So Nick, that tells us what about lithium? 3 protons and 3 electrons, right? So we got to place 3 electrons here for lithium, all right? Eris, what order do these orbitals get filled according to this chart?
Like one
Well, where do we start?
bottom.
Bottom, right? So, just like in the last two, what's the first orbital that we come across? 1s, right? Line 1s. Okay? Eris, how many electrons can that orbital hold? 2. There's 1, there's 2. But, for lithium, how many electrons do we have to place? 3, right? So, we go back to our chart. We go up the chart, right? So we said bottom to top. What's the next orbital that we run into? 2s. Another line, right? But now we're going to label it what? 2s. Quick, 30 seconds. The fact that we call this orbital 2s should be able to tell you 2 things about it. Discuss with the person next to you. Go. All right, so the fact that it is labeled 2s, what can you tell about it? The fact that it's labeled 2s, what can you tell about it? Besides Mark. Come on. It's okay, you can tell me. It's all right. 2s, what does it mean? I heard you guys talking about it, and some of you were talking about it correctly. What does it mean, 2s? Go ahead. Come on, Jordan. Break the ice for us. Go ahead.
It's the second sublevel.
Okay, how about the second orbital, right? Or the second energy level is a better way to describe that, okay? So, that being the case, Jordan, what does that tell you about the energy of electrons that are in it?
It's still lower, but it's not the lowest.
It's not the lowest, but it's still pretty low, because it's going to be where? Where is this orbital going to be located?
The second one away from the nucleus.
Second one away from the nucleus. So still pretty close to the nucleus, right? Okay. That's the 2 part. What does the s part tell us? What does the fact that it's an s orbital tell us? Go ahead. It's a spherical shape as well, right? So this is going to be like our second shell, right? Around that first orbital, okay? All right, good there? See, we can answer questions, really, we can. I have faith in you guys, okay? But more importantly here to our focus right here, right? What's going to go in that 2s orbital? Well, how many electrons do we have to place for lithium? 3. How many have we placed so far? 2. So that means that how many electrons are going to be in this orbital? Just 1. There is our orbital diagram for lithium. Okay? Good there? All right. So, next, I believe the next one on your list is beryllium. Is that right? Boron? Okay, we go to boron. Okay. All right. So, let's go boron. All right, so you find boron on your periodic table, right? What do you find out about boron by looking at it on the periodic table? Eris, go ahead.
Atomic number is 5.
Atomic number is 5, and that's telling us what?
That 5 electrons.
5 electrons that we have to worry about here, right? 5 protons, 5 electrons, okay? So, there's our chart, right? Start from where? Start from 1s, because where is 1s on the chart, Suzanne? Bottom, right? So, start line 1s, right? We've already established how many electrons can that 1s orbital hold. 2. 1 up, 1 down. Okay? Next orbital that we come across on the chart is what? What's the next lowest energy orbital? 2s. Line 2s. Okay? How many electrons can that orbital hold? 2, right? 1 up, 1 down. Okay? Next orbitals that we come across are what? P. Specifically, which P? 2p, right? 2p orbitals, right? What can you tell me about 2p orbitals? The fact that they are 2p. Okay, so we said that p orbitals, right, have that sort of, that's not what I wanted. P orbitals have that kind of like figure 80 shape, right? And we said, how many p orbitals are there? If you go back to your chart, Eris, go ahead. There are 3, right? We said one runs x-axis, one runs y-axis, and one runs z-axis. Okay? So there are 3 of them. And if you look at your chart, how many lines are drawn next to 2p? There are 3 lines. Okay? When we start getting to p sublevels, there are rules about where electrons go within those p orbitals. And again, it's related to energy. Okay? Whenever we get to a p sublevel, we draw all 3 of those lines. Okay? And then we label each of them as the p sublevel. So each of these would be labeled as 2p, 2p, 2p. Okay? How many electrons do we have left to place? 1. But how many possible locations do we have for that electron? 6 possible locations. Does it matter where we put that one electron? Any guesses? The answer is no. It doesn't matter where we put that one electron. If we look at this chart, right, what do you see about all 3 of those lines? How high are they up on the chart compared to each other? They're all right next to each other, right? There is no p orbital here that has more or less energy than the other 2. So with that being the case, that electron can go anywhere within those p orbitals. Generally, we draw it in the first one, but it wouldn't be wrong if you drew it in any of the other places. Okay? Would it be wrong if I did this? Would that be wrong? No. That's fine. The up and down only is important if we're talking about 2 electrons within the same orbital. But if you only have 1 electron in an orbital, it doesn't matter what you do with it. You can pretty much put it anywhere you want to and draw it anywhere you want to. Okay? But it does become important when we start talking about our next element. So the next element that we come across, I believe, is carbon. Is that correct? Is that the next one on your outline? Okay. All right, so carbon. Okay? Find carbon on the periodic table. Atomic number is what? 6. So 6 electrons that we have to place, right? Where do we start? Where are they most likely to go to begin with? Okay, start at 1s, right? It's the lowest on the chart. 1s can hold how many electrons? 2. 1, 2. It's the most likely location to find electrons. Okay? Next, what's the next lowest orbital that we come across? 2s. Line. 2s. How many electrons? 1, 2. Okay, now we're up to how many? 4. Next set of orbitals we come across. 2p. 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 Okay. Here's where it becomes important where we start writing electrons. Okay? On your outline underneath carbon, you have the details about something we refer to as Hund's rule. Okay? What does it say about Hund's rule underneath carbon on your outline? Give me the gist of what Hund's rule is. Mark, go ahead.
You can't have, if you have a sublevel with, if you have an orbital with multiple sublevels, you can't have two electrons in one of those orbitals if the other ones don't have any.
Gotcha. So, two ways we can look at it. One, electrons will spread themselves out as evenly as possible as long as they can. Why? What do all electrons do to one another? They repel each other. So they want to try and spread out as much as they can. Second, electrons, each orbital can hold 2 electrons. But they won't start pairing up until they have no choice whether or not to pair up. Okay? So we said that in boron, we drew electron number 5 right here. Is this p orbital full? No. It can hold how many electrons? It can hold 2. But is electron number 6 going to go here? It is not. It's going to go here. Okay? Is that the only possible place for it? Nope. Could go where if we wanted it to. Could go over here if we wanted it to. Right? Thanks. Could go over here if we wanted it to. What else could we do with it if we wanted to? Mark?
Flip it upside down.
Flip it upside down, right? It really doesn't matter. Okay? Generally, we see it filled in this way, and if you see it in the book, that's fine. But this answer is not any better than this answer, and this answer is not any better than the original answer. It's all the same, because all of these electrons, all of these orbitals have the same energy. Okay? Does that make sense? We okay with that so far? All right. Let's finish off here with just one thing, okay? And then we will get into the next part, okay? So I'm going to jump ahead a little bit. This isn't the next one that's on your sheet, but I'm going to do it to make a point. And let's do sodium. Okay? So find sodium on your periodic table. Okay? 11. All right? That means we have 11 electrons that we have to place. Okay? Now, the end result, okay, I'm not doing this one necessarily for the end result. I'm doing this one for a little bit of order, okay? You don't have to draw it this way, the way I'm going to show you, but I'm going to do it to make a point, okay? So, 11 electrons, right? Where do we start? What's the lowest energy orbital that we always start with? 1s, right? So 1s, okay? 1 electron, 2 electrons, okay? What's the next lowest energy orbital that we come across? 2s is next, okay? 3, 4, okay? Good so far? All right. Next energy orbitals that we come across, what's the next lowest energy? 2p. How many 2p? 3. 1, 2, 3. 2p, 2p, 2p. All right? Now, the end result of this, like I said, the end result, I'm not going to be able to tell whether you write it this way or not, but I'm going to do it this way just to show you what we're talking about. Okay? So, here's number 5. Here's number 6. Here's number 7. Okay? That's how 7 electrons would distribute themselves. Hund's rule says that all 3 of these will get 1 electron before any of them get 2. Okay? But how many electrons can each of those orbitals hold? 2. Are any of them full yet? They're not. Now they will start pairing up. Okay? Here's 8, here's 9, here's 10. Okay? Now, if you don't do it in that order, like if you don't fill them that way, if you just drew up, down, up, down, up, down, up, down, would I be able to tell the difference? No, I wouldn't like on a test, all right? But for demonstration purposes, that's the order it would go, okay? But how many electrons do we have to fill? We have to place 11, right? So we go back to our chart, we start at the bottom, 1s was the first place, 2s, 2p, what's the next orbital that we come across? 3s. So, there, 3s, how many electrons does it get? Just 1. Good there? There, it's good.
What's the noble gas notation?
We will talk about that tomorrow. Okay, yeah, I'll finish that up tomorrow. Okay? Yeah, that's the reason why I wanted to get this to you now, but we'll get to that tomorrow. Okay? Alright, so for tonight, might be a good idea to start looking at some of that sheet that I gave you, the other sheet. The answers are posted online, although technically we'll make it tomorrow night's homework. But you should be able to start looking at some of it now. Answers are posted online. Okay?